In this video, we are going to talk about heat change at constant pressure. In the previous video, we talked about heat change at constant volume. In this video, we are going to focus on another aspect of heat change, that is at constant pressure. Now, there it was equal to internal energy, but in this case, it is equal to enthalpy. Okay, now how we proceed. As we did for the constant volume, here again, we are going to use the first law of thermodynamics. So again, only considering the pressure volume work, the first law will come out to be of this particular format. This we have already seen in the previous video. Okay, so now at constant pressure, we can kind of expand this expression to this particular format because we know it's a finite change and these are state functions. So it only depends upon the initial and the final values. And if suppose 1 and 2 represent the initial and the final state of a system, you can write delta U as U2 minus U1, that is final minus the initial value of the state function. So internal energy, you can write it as U2 minus U1. Then you can then we have the QP, since we are considering this at constant pressure. Therefore, we are going to write a subscript P here as we did for the constant volume. Now, thereafter, P is constant, so there is no variation in value. And then delta V, again, a state function depending upon the final and the initial states. Therefore, we have V2 minus V1. Okay. Now, this equation can be a little rearranged. For example, we can bring this PV2 term here, similarly PV1 term here. So accordingly, our expression would look something like this in the rearranged format. Okay, now if you look here, we have a combination of state functions here, that is U is a state function, P is a state function, V is a state function. So obviously a combination of all the state function is also a state function. And therefore that new state function, that is the summation of internal energy plus the product of pressure volume, is actually a state function because all of these terms are a state function. And therefore this new state function, which is the combination of U plus PV, is actually, we call it as enthalpy, and it is represented by a symbol capital H. And therefore, this represents the final state, so we will call it as H2. This represents the initial state and therefore the H1. So what you see here is the heat change at the constant pressure is equivalent to the change in enthalpy. Okay, so again, I'm going to recap what we did in the previous video, that the heat change at constant volume was equal to the change in internal energy. But here, when it is that heat change is happening at a constant pressure, it is equivalent to a change in enthalpy. So the statement comes here that heat absorbed or evolved at a constant pressure is a measure of the change in enthalpy. So this equation is very, very important. Okay, so like constant volume, constant pressure also is very, very important. Now, before we close this video, I would like to also talk about the relationship between enthalpy and the internal energy. Now, enthalpy, as we just now defined, it's a combination of internal energy plus the pressure volume. So H is nothing but, according to definition, it's equal to U plus PV. Okay. Now, when you introduce finite changes in enthalpy, for example, you add a delta symbol here, so you end up in delta symbol H. So this represent this for the finite changes. So delta H is equal to delta U plus this would be taken as a whole. So delta product of pressure and volume. Now, this since involves two state functions, when you open up, you can treat this finite changes in two aspects. One is happening at a constant volume. Another term is happening at a constant pressure. So that means each time you apply the finite change, it would be that one of the term would be a constant and therefore coming out of the finite symbol. Okay, so accordingly, you have delta U plus V delta P plus P delta V. Okay. Now, if we consider a case of constant pressure, that means constant pressure means there is no change in pressure value. So delta P should be equal to 0. In that case, this particular expression will reduce to delta H equals delta U plus P delta V, because this term will vanish because delta P is 0. And therefore, we have an equation that is delta H equals delta U plus P delta V. So this is an important relationship that is quite often asked in the question about the relationship between delta H and delta U. So you might be required to derive this in this particular format. Now this equation can be again written as QP, because we know that a heat change at constant pressure, we can write it as QP. In the same way, heat change at constant volume, we can write it as QV. So this equation can be rewritten in this format also. QP equals QV plus P delta V. So this equation, this set of equation is very, very important. So please try to keep this relationship in your mind. Okay, now let's try to understand some inferences from this particular expression here. Suppose our delta V value is positive. So positive means you are having a case where there is expansion in the gas. Okay, so when you have delta V positive, then that means your delta H value would be higher than the internal energy, because delta H is now an internal energy plus some value. So therefore, obviously, delta H would be higher than the internal energy. If suppose your delta V is negative, so that means it is undergoing compression. Okay, so compression means here that would be a negative term. So obviously, in this case, delta H would be less than the value of the internal energy. And then if suppose there is no change in volume, that means you're considering a constant volume situation, this term will vanish and you are left with now only delta H equals delta U. So that means in conditions involving constant volume, both delta H and delta U are the same. And this can be hypothetically realized, especially in the case of solids and liquids, because we know that the change in volume that can be brought about in solids and liquid would be very, very marginal, because they do not compress or expand easily as you see the gases. And therefore, the delta V term would be negligibly small. That means you can think of this term completely not there, because delta V is very, very small. So it is, the second term would be infinitesimally a smaller value. In such cases, especially in solids and liquids, you can expect the delta H and delta U to be approximately of the same value. Okay, so I hope you have understood in this video the heat change that is happening at constant pressure, and at the same time you understood also the relationship between delta H and delta U. Please go through these derivations, practice them so that you should be comfortably able to derive them. And that's it for this video, and have a nice day. Thank you.